Okay, I'm going to walk you through the solutions to the Cive1460 Exam Question 3 Water Engineering question. So let's just write that down. Cive1460 Exam June 2024 Question 3 Water Eng. Okay. Right. First question. Express this pressure of 35.5 meters of water in these three units: newtons per meter squared, bar, pascals, actually 4 units, and in meters of mercury. Okay, so let's just write this down. We've got 35.5 meters of water is the pressure. What's the equivalent in terms of newtons per meter squared? Bar, pascals, and meters of mercury. So let's just say what we've got in terms of data. Rho of water, rho of H2O, we're told to use 1000 kilograms per meter cubed. Use G as 9.8 meters per second squared. And the relative viscosity, relative density of mercury is equal to 13.5. So rho of mercury is 13.5 times 1000, which equals 13,500 kilograms per meter cubed. Okay, anything else from the question? No. So let's see. A in newtons per meter squared. So all we apply is our usual equation, P equals rho GH. Well, we're going to use rho of water, so 1000 times 9.8 times 35.5, and that comes to P equals 347,900 newtons per meter squared. Right, straightforward. B, in terms of in bar. Now what do we know? We know that 1 bar equals 10 to the 5 newtons per meter squared, which equals 100,000 newtons per meter squared. So 347,900 divided by, we could have written this as 347,900 times 10 to the minus 5, but this equals 3.479 bar. Okay. C, in pascals. Well, 1 pascal is equal to 1 newton per meter squared, so this is really very straightforward. P equals 347,900 pascals. Okay. And the last part of the question, D, in meters of fluid, well actually it's named as of mercury, with rho Hg equals 13,500 kilograms per meter cubed. So P which we know is 3, 4, 7. Well, let me just remember what it was. 347,900 is equal to rho of Hg times G times H. We could possibly let's say H of Hg. So 3, 4. So H of Hg 347,900 divided by 13,500 times 9.8 equals 2.63 meters. Okay, that question completed. Let's just look at the number of marks. There's 4 marks, so there's 1 mark for each one of those. Okay. Question B. There's a part B of this question. With reference to velocity profiles and pressure gradients, describe why boundary layer separation occurs. Boundary layer. So this is the key thing we're describing. So let's use diagrams and then sketch 4 likely situations where boundary layer separation will occur. Okay, so what we've got to look at here is how to describe boundary layer separation. So boundary layers occur, so we need to start by the fundamentals. Boundary layers occur because you get a slowing of the velocity at a boundary. So in this diagram, say we've got a wall, a boundary, fluid flowing past it. This will cause the velocity to be 0 at that wall, and we'll get a velocity gradient. So slow, faster, flow, velocity of flow. Okay, and it's because of this phenomenon that we're going to get some boundary layer separation. Clearly, this slower flow has lost some energy because of the boundary, because of friction. We might just want to note that we have Newton's law of viscosity, that the shear stress flowing in the fluid can be derived from this equation, where that du dy comes from the gradient of this diagram, du. Okay, it's not so important in this description, but in similar description questions it is. So, why boundary layer separation occurs? Well, fundamentally it's because we've got this interaction with the boundary. But what we can do is say, well, the next thing we know why boundary layer separation occurs is because we have this situation in, for example, a divergent flow. So a pipe that's going flowing in this direction and then flows out. It goes from narrow to wider. So from continuity we have Q equals U1A1 is equal to U2A2. Now because A gets smaller, A2 is much bigger than A1, that leads to U2 being much less than U1, Okay, so this is slower flow. Now, because of the Bernoulli equation, let me just write down this Bernoulli equation. This is an important thing to note, to include in an answer like this. P1 over rho g plus U1 squared over 2g plus Z1 equals P2 over rho g plus U2 squared over 2g plus Z2. we've got a horizontal situation like this, we can ignore those two. Now, if we know that U2 is smaller than U1, so if this term has got smaller, this term must be bigger. So pressure has increased in the direction of flow. So P2 is greater than P1. Higher pressure at this end. So a summary of this situation is that we have high velocity, low pressure, low velocity, higher pressure. So higher pressure here is potentially able to push back this way. So a diagram where we might want to add on to that diagram is to put our velocity profiles. So we have these velocity profiles as this flow is entering the divergent section. We have slow flow here. And as we've got a high pressure, higher P2, pushing back here, it is sometimes, if this slow flow is not fast enough, can lift this boundary layer and actually reverse the flow just near the wall and lift this slower moving flow into the main body. And that's what boundary layer separation is, and that's why and it's because it occurs particularly in divergent sections and can be explained by the continuity and the Bernoulli equation. Okay. The question asks for 4 diagrams of situations where boundary layer separation may occur. Well, I've restricted it here to pipes. We've got an 90-degree T section. Because you've got an increasing of the flow area, this section, you get slower flow and higher P. So you get a bit of a potential for flow to be pushed back there, and similar situation here. Pretty similar for the divergent junction. High and it's all because you've got an increase in the flow area. A very sharp bend, like this U bend, again you've got an increase in the flow area here. Where you've got an increase in the flow area, you get reduction, lower U, higher P. So you got this flow there, and the same on this exiting bend. Last example is flow past a cylinder. Remember, civil engineering, you do see cylinders, you see columns, they're very rigid, but you also use cables, for example on cable stay bridges, suspension bridges, and the flow around the boundary layer separation coming off cylinders or cables can cause these things to vibrate. So this question is not asking you for too much detail on these 4 examples, just examples saying where you may get boundary layer separation. Okay. At part C of this question is a fairly straightforward question, calculation of the force on a gate, and then calculation of the moment due to the force on the gate due to the water. But this has got a slight variation, because it's saying, well, how much force is required to open that gate? So let's just see what this actually is asking. So we've got a square gate. Here we are, square gate. side length to 2.5. So here's our gate. Can actually draw it here. Square gate, 2.5 meters by 2.5 meters. Hinged at the top, vertical wall. This makes things a bit simpler. It's down at a depth of 4.5 meters to the hinge. It says what force F is required to open this gate. So what do we know? We know that we'll have a resultant force R acting on the gate due to the water. We have a position here in the middle that we've often labelled G, the centre of gravity or the centroid, and that R acts at CP, centre of pressure. So R will impart a moment on this hinge, and F needs to overcome that moment. So we need to find R, we need to find CP. Might just draw some labels extra on this diagram now. We can draw dimensions here. That this depth is SC, the depth to the centre of pressure, and we have a line down to the centre of gravity, which is Z bar. Okay, we only need to calculate those. So, what's R? R is equal to the, as always, pressure at the centroid times the area. R equals rho G Z bar times A. Z bar is equal to, well, we can see that 4.5 plus, well, it's halfway down the rectangle, so it's 2.5 over 2. So Z bar is 5.75 meters. A, well, that's simple, 2.5 times 2.5, so 6.25 meters squared. So R, simply 1000 times 9.8, so 1000 because we've got water, times the Z bar, 5.75, times the area, 6.25. Do the calc, 352,187.5 newtons. We'll put this down to 4 significant figures for this question. Or in terms of kilonewtons, 352.2 kilonewton. Okay. So we're going to calculate the position of the centre of pressure. SC, using the familiar formula, IgG, second moment of area of the shape about its centroid, over a x bar plus x bar. Now, because it's vertical, x bar equals z bar, which equals 5.75 meters as above. IgG for a rectangle is BD cubed over 12. We can look that up in a table. 2.5 times 2.5 cubed over 12, which works out as 3.255 meters to the 4. And then we can calculate SC. 3.255 over 6.25 times 5.75 plus 5.75, which equals 5.841 meters. So R acts at 5.74 meters below the surface. Okay, next bit of the question, we need to calculate the moment. Now let me just draw the sketch, this diagram. We've got SC coming down. We've got a gate here. We've got this gate height of 2.5 meters. We've got a force acting here, F. I'll do the reaction force here, R. I'll just tidy up that SC so it actually goes to the R. Oops. SC goes down to R. Okay, now what moment is this causing? R is causing a moment round here, so that's M. M is equal to L times R, where L is this lever arm, and L is equal to SC minus, well, the depth to the hinge, which was 4.5 meters. So L equals 1.341 meters, because SC was 5.841. Okay, it is in full. Right, so the moment, I'll revert to black here, the moment equals 1.341 times the reaction force, which was 352,200. To give us a moment of 472,300 Newton meters. Now the moment due to F, the moment to be for opening the gate, must be bigger than that. So F must be F times the gate height, 2.5, has got to be greater or equal to 472,300. So F has got to be greater than 472,300 actually. Over 2.5, which equals 188,920 newtons. And that's the answer. That's the force required to open the gate.